Solving general chemistry problems. Electrochemistry. Fluorine is the atom with the largest electronegativity in the periodic table. It becomes very stable when it accepts an additional electron. Because of that, the reduction of fluorine gas to fluoride has one of the most positive standard reduction potentials, and is usually the reaction that lies at the top of the table. By contrast, the alkali metals and alkaline earth elements are all greatly stabilized by giving up their valence electrons. While the details can be complex, it turns out that the oxidation of lithium has the largest oxidation potential. Therefore, it is commonly found at the bottom of these tables with the most negative standard reduction potential. The reduction of hydrogen is assigned an SRP of 0 volts exactly. Here is some language around redox processes that is worth understanding. Substances up in the table on the left-hand side are easily reduced. Substances low on the table on that same side are difficult to reduce. Substances low on the table but on the right-hand side are readily oxidized. Entries high on the table on the right-hand side are difficult to oxidize. In truth, these generalities need to actually be understood in light of a specific pair of reactions. It really is their difference that is most important. Now note the following words and their use. F2 is easily reduced. It's an excellent oxidizing agent. It's an excellent oxidant. Lithium is easily oxidized. It is an excellent reducing agent, an excellent reductant. F- is very difficult to oxidize. It is a poor reducing agent, a poor reductant. Lithium plus is very difficult to reduce. It is a poor oxidizing agent, a poor oxidant. Notice how when something is readily reduced, we refer to it as an oxidant or oxidizing agent. It induces oxidation in something while it itself is being reduced. A similar argument for reducing agents can be made. And don't forget that when we talk of something as being a good or poor reductant or oxidant, it must be in comparison to another specific reaction for that to have meaning. It is the difference in reduction potential that is important. We say that fluorine is a very good oxidizing agent. That is simply because there are so many things below it in the table. H plus can also be an excellent oxidizing agent, but only for those substances below it in the table. When chemists are developing a chemical reaction, they might need something to reduce the species of interest. They will say they are looking for a strong reductant. They may not need to specify lithium, for instance, but they will look for something in that region of the table. Let's look at some questions you might encounter in general chemistry. Now consider these two entries from a standard reduction potential table. We've got gold 3 plus reducing to gold and copper 2 plus reducing to copper. You have two pieces of metal, gold and copper, and two flasks with two solutions, gold 3 plus and copper 2 plus. Which combination of materials will lead to a chemical reaction occurring? Gold 3 plus and copper 2 plus? Gold and copper? Gold 3 plus and copper? Copper 2 plus and gold. Think about it for a minute and then make a choice. Well, the answer is C. Gold 3 plus will be reduced and gold will start to plate out on the copper electrode, and the copper electrode will start to be oxidized and dissolve into the solution, forming more copper 2 plus. The driving force for gold 3 plus to reduce to gold, which is plus 1.52 volts, is more than enough to drive the oxidation of copper metal, minus 0.34 volts. It's negative because the reaction is the opposite of the reduction process given in the table. For A, both species are already fully oxidized. No possibility for one of them to be further oxidized. For B, both species are fully reduced. No possibility for one of them to be further reduced. And for D, copper 2 plus's ability to reduce is insufficient to drive the oxidation of gold. Something on the left will react with something on the right that is more negative, less positive than itself. Now here's another. Consider these two reduction half reactions. Use them to produce an electrochemical cell under standard conditions. We've got chlorine gas reducing to chloride and tin 2 plus reducing to tin metal. Which half cell will be acting as the cathode, that is, the half cell where reduction will be occurring? The reaction with the most positive reduction potential will be the cathode. In this case, it is the chlorine half cell. As the reactants are a gas and an aqueous ion, an inert electrode will have to be provided. We can imagine a platinum electrode, for instance, being used to make the connection to the positive terminal of the voltmeter. Which species will be increasing in the amount of it that is present? chlorine, chloride, tin 2 plus, or tin. Now the chlorine reaction will be proceeding as a reduction, and the tin reaction will be as an oxidation. Therefore, B, chloride, and C, tin 2 plus, will both be increasing in concentration. The chlorine gas and the tin solid will both be decreasing. What will be the measured cell potential? Plus 1.497, plus 1.223, or minus 1.497, minus 1.223? Well, cell potential is calculated as cathode minus anode. So in this case, E naught is 1.360 minus a minus 0.137, which is plus 1.497 volts, or A. Well, here's another question. Consider these two entries from a standard reduction potential table. We've got sulfate reduced to form sulfur dioxide, and indium 3 plus reduced to form indium metal. What will be the cell potential? Minus 0.508, minus 0.168, plus 0.168, or plus 0.508? Well, the answer is D, plus 0.508. The most positive reaction will be the cathode. The cell potential will be calculated as cathode minus anode, or E naught cell is 0.17 minus a minus 0.338 for plus 0.508 volts. Write out the overall balanced chemical reaction. Well, to do this, we need to get the same number of electrons in both reactions, then write the anodic reaction in reverse so it is an oxidation, then combine and cancel. Multiply the sulfate reaction by 3 and the indium reaction by 2. Reverse the anodic oxidation reaction, the one with the least positive, the most negative reduction potential. Add them together, cancel any excess. Always quickly check that all atoms balance and that the overall charge balances, as it does in this case. Here is another. Consider these two reduction reactions. Form them into a cell. What is the measured standard cell potential? What's the overall balanced chemical reaction equation? Well, here we have nitrate being reduced to nitrous oxide and nitrate reduced to nitrite ion. Both equations involve the nitrate ion. One goes to nitrous oxide, the other to nitrite. The most positive is still the cathode. The cell potential is still cathode minus anode, 0.956 minus 0.009, or plus 0.947 volts. To obtain the balanced reaction equation, first scale them to get the same number of electrons in each. Multiply the first by 2 and the second by 3. Reverse the anode reaction, the least positive one, to make it an oxidation. Add them together. Cancel electrons. Cancel excess nitrate ions. Combine the 3 waters and the 4 waters on the right-hand side to get 7 waters in the product. Note that on the left, the hydroxide and hydronium ions can be combined to form water. OH plus H plus goes to H2O. Combine them. Note that there are more hydronium than hydroxide. Cancel all this excess water, and this is then the final balanced reaction equation. Check that the atoms and charge balance. Now this was a more challenging exercise. Think back to how we had to balance reaction equations. Imagine if you were given the final equation unbalanced and had to figure out the 2 half reactions. That would be challenging, right? Now I remind you that these tables can also help to determine reactivity between molecular systems. When you mix 2 things together, by finding the right reduction reactions, we can assess if a reaction will occur or not. Here are a series of mixing processes. Use the standard reduction potential data to determine if a reaction occurs. Now we've been given 6 situations here to consider, and we'll deal with them one at a time. And here's the relevant standard reduction potentials that we'll use. We'll pull them up each time for each question as it's needed. Now first, metallic tin in hydrochloric acid. As reactants, we have solid tin, aqueous chloride, and aqueous hydronium ion. Here are the relevant reduction potentials. When we're making a cell, we would take the most positive reaction and assign it to be the cathode. In these problems, we instead have to arrange the reactions in pairs based on the reactants that are present. We arrange the equations so that the reactants are on the reactant left-hand side of the final equation. We still need, however, to combine a reduction with an oxidation. Chloride is a reactant. We need to switch that reaction equation. It will now be an oxidation. H plus is a reactant. That equation remains as it is. It's a reduction. And tin is a reactant. We switch that equation. It will be an oxidation. Now consider all pairs of reactions between these three. Tin won't react with the chloride as there is nothing to reduce in that reaction. H plus and chloride is a redox reaction, but E naught equals 0 minus 1.36 or a minus 1.36 volts. The negative potential indicates that it will not react. H plus and tin is a redox reaction. E naught equals 0 minus a minus 0.14 or plus 0.14 volts. The positive potential indicates that it will react. Tin will dissolve in the acid solution by reaction with the hydronium ion, but not because of reaction with the chloride ion. Here, add metallic tin to a solution containing chlorine gas at 1 bar pressure. Reactants are just solid tin and gaseous chlorine. Here are the standard reduction potentials. We need to switch the tin reaction so it becomes an oxidation. The chlorine reaction remains as it is. It is a reduction. Only combination possible gives E naught equal to 1.36 minus a minus 0.14 or plus 1.50 volts. Reaction occurs. Tin will dissolve in the solution of chlorine gas. Add zinc to a solution of tin 2+. And I assume you are starting to get the routine here. Rearrange the equations so that available species are on the reactant side. Consider all reduction-oxidation combinations. Any positive reaction potential will react. The trick here is that tin 2+ shows up in two reactions. In one it is a reductant and the other an oxidant. Tin 2+ reducing to tin is the only reduction equation. The other tin equation also has tin 2+. Now it makes no sense to mix it with itself, so we will ignore that reaction. Only consider mixing with zinc. That redox reaction has a standard reaction potential E naught of minus 0.14 minus a minus 0.76 or plus 0.62 volts. Reaction potential is positive. Reaction will occur. Zinc metal will dissolve in a tin 2+ solution. Now, add 1 molar iron chloride to a solution of tin 2+. We've got iron 3+, chloride ion, and tin 2+ that are present. Again, there are two tin 2+ equations and two Fe3+ equations, 5 equations total. Here they are. Now, switch the chlorine and the 1 tin equation around to get all the reactants on the correct side. There are 2 oxidation reactions and 3 reductions, 6 possible redox combinations. As before, mixing tin 2+ with itself makes no sense. We only need to consider possible reactions. Now I'll number them to make them easier to follow. So oxidation reaction number 1 will be combined with the 3 reduction reactions, which is 2, 4, and 5. We will calculate the reaction potential. If any are positive, then reaction will occur. Here are the 3 results. Now note that all of them do not react. The oxidation potential of the chloride is just too large. Now try the tin oxidation, which is reaction 3, and pair it with the reductions 2 and 4. Again, pairing with 5 makes no sense. Here are those 2 results. So yes, there will be one reaction. Iron 3+ will be reduced to iron 2+, and tin 2+ will be oxidized to tin 4+. And so now we have the one more. They've got the add metallic zinc to tin 4+ solution. Identify the reactants and retrieve the relevant equations. Switch the zinc equation around to get metallic zinc on the reactant side. Only one possible combination. Reaction potential is positive 0.91 volts. It will react. Now, the only wrinkle to add to this question is to note that when the tin 4+ reduces to tin 2+, the tin 2+ can further react with the zinc, we saw that earlier, and reduce to metallic tin. So the end result is zinc dissolving and metallic tin plating out of the solution. And finally, here we bubble chlorine gas at 1 bar pressure through a solution of tin 4+. Here are the reactants and the equations. But there is a problem. The reactants are both already on the reactant side. They are both reductions. There is no oxidation to couple to. There is no reaction. And here's the last equation we'll look at here. And now, instead of taking a series of equations and predicting whether or not a reaction will occur, in this case, we will take a series of experimental observations and deduce the relative ranking of the reduction potentials. So this is what is observed. We've got 5 observations. Solid iodine and solid sodium react with each other. A solution of gold plus and I minus reacts. A silver ion solution reacts with sodium. Gold and silver ion do not react. Finally, silver and iodine do not react. We want the relative ranking from the most positive to the least positive. Look over the substances involved and realize that there are 4 standard reduction potential equations we must consider. Here they are. I will label them so we can keep track of them more easily. The reduction of sodium ion, reduction of iodine, reduction of silver ion, and the reduction of gold ion. Consider what the 5 observations imply about their relative ranking. First, iodine and sodium react. Well, sodium must be oxidized. Thinking back to our strategy earlier, a reactant on the left-hand side of the table, iodine in this case, will react with an entry on the right-hand side, sodium in this case, only if the reduction is higher in the table. Our conclusion is that iodine is more positive than sodium. The gold plus and I minus react. And this time the iodide is the reactant along with gold 1 plus. Reaction is observed, so the gold reaction must lie higher than the iodine reaction. Gold is more positive than iodine. Silver ion and sodium react. Silver ion is reduced, sodium is oxidized. Silver must lie higher in the table. Silver is more positive than sodium. Gold and silver ion do not react. Well, if there was a reaction, silver would have to be above gold. Since there is not a reaction, gold must lie above silver. Gold is more positive than silver. And silver and iodine do not react. If they did react, iodine would be higher than silver, but since they do not, silver must be higher than iodine. Conclusion, silver is more positive than iodine. Put this all together. Here again are the 4 reduction equations labeled to keep them straight. Observation 1 indicates that iodine is more positive than sodium, or that equation B must be higher than equation A. Observation 2 places gold, reaction D, above iodine, which is B. Observation C places silver above sodium, but it is not yet clear where it sits with respect to the others. Observation 4 confirms that gold must be the highest, though silver relative to iodine is not yet clear. Finally, observation 5 confirms that silver is higher than iodine. The correct ranking is shown, along with standard reduction potentials taken from a table, which confirms our ranking.